You know, when we talk about electronics, it's easy to get impressed by raw, untamed power. But honestly, that's almost useless on its own. The real magic, the thing that truly matters, is control. So today, we're going to dive into this really elegant engineering idea that's all about trading that brute force for absolute precision. It's how we turn unpredictable parts into amazing, high-performance systems. So here's the big question, right? How do you do it? How do engineers build something that works perfectly every single time when the very components they're using are, well, kind of flaky and unpredictable? It's like trying to build a Swiss watch using parts that literally change size with the weather. It sounds impossible. But the solution is a concept that is as powerful as it is simple: negative feedback. Okay, let's get down to it. At the heart of most electronics, you've got the amplifier. Its whole job is to provide gain, to make a signal stronger. But here's the thing about a basic raw amplifier. It's kind of like a wild beast. Its performance can drift all over the place with a small change in temperature, or even tiny invisible variations from the factory. So yeah, it's got power, but it has absolutely no discipline. So how in the world do you tame that wild beast? Well, engineers came up with this really simple but totally profound idea. You take a tiny sample of the amplifier's output and you loop it back to the beginning to help correct the input. This self-correcting loop, that's the whole essence of negative feedback. It's what brings order to all that chaos.
And here it is, the core idea. It is all about subtraction. That's the key. By constantly subtracting a small piece of the output from the original input, we create something called an error signal. The amplifier then just goes to work trying to make that error as small as possible. And in doing that, it forces the output to become a perfect scaled-up version of the input. It's brilliant.
And you know, what's so cool about this is just how simple it looks. You've got your main amplifier, right? That's the powerhouse. We'll call it A. Then you have this simple little feedback network, which we'll call beta. Its only job is to just sample the output and send a little fraction of it back to the start. That one simple connection creates the entire control system.
And this brings us to what is, without a doubt, the most critical number in this whole discussion, the loop gain. It's super simple to calculate, just the amplifier's gain, A, multiplied by that feedback factor beta. This one value, A times beta, tells us basically everything we need to know. It tells us how much control we have, how stable the system is going to be, and just how close to perfect we can get.
This is just a perfect way to think about it. I mean, you don't just point your car in one direction, floor it, and close your eyes, right? Of course not. You are in a constant feedback loop. Your eyes are the feedback network. They're constantly sampling your position on the road. Your brain calculates the error, whoops too far to the left, and your hands on the wheel are the correction. Negative feedback in a circuit is just the electronic version of staying in your lane.
So we give up some of that raw power, some of that gain, to create this control loop. And you might be asking, why would we ever make that trade? Well, because what we get in return is so much more valuable. In fact, you could say we gain 4 distinct superpowers.
And these are the big 4. By using negative feedback, we make our gain totally stable and predictable. That's huge. We also stretch out the range of frequencies the amplifier can actually work with. We slash distortion, so the output is a much cleaner, purer copy of the input. And we get precise control over the circuit's input and output resistance. It's a total game changer.
Okay, so the first superpower is predictability. Without feedback, you've got the thing on the left, a flaky, unpredictable mess. Its gain might be 1,000 today, but tomorrow, when the room warms up a little, maybe it's 950. Who knows? But with feedback, you get the system on the right, a polished, rock-solid, reliable device. The gain might be a lower, stable 100. But guess what? It's going to be exactly 100 today, tomorrow, and on every single unit that comes off the assembly line.
This is another fantastic trade-off. Think about it like this. Without feedback, your amplifier is like a cheap subwoofer. It might be really loud, but only for a very narrow range of deep bass notes, like that sharp peak you see on the graph. But once we apply feedback, we get the speaker on the right. We sacrifice some of that raw, peaky volume in exchange for high fidelity across the entire musical spectrum, from the deep bass to the clear mids to the sparkling treble. We trade a little loudness for a much wider range.
Now, it's important to know that feedback isn't just some one-size-fits-all thing. Not at all. Depending on what you're building, whether it's an amplifier for voltage or for current, or something else, you have to connect that feedback loop in very specific ways. These different connection styles are called topologies.
This table lays out all the options, and there's a really simple rule to remember. Connecting in series makes resistance go up, and connecting in shunt, which is just another word for parallel, makes resistance go down. So, okay, let's say we want to build a perfect voltage amplifier. What do we need? Well, we want it to sense the input voltage without messing with it, so we need a huge input resistance. And we want it to deliver its output power without any loss, so we need a tiny output resistance. We just look at the chart, and there it is. The series shunt topology gives us exactly that. High input resistance, low output resistance. Each one of these is like a specialized tool for a very specific job.
So up to this point, negative feedback seems like this perfect magical solution, right? But it has a dark side. There's a critical vulnerability, a catch that every single designer has to worry about. The very thing that gives us all that amazing control can, if we're not careful, cause a total catastrophic failure.
It all comes down to this one question. That feedback loop, it isn't instant. It takes a tiny, tiny fraction of a second for the signal to travel from the output back through the feedback network to the input. And at really high frequencies, that tiny little delay can suddenly become a huge, huge problem.
And here's where it all goes wrong. If that delay is just the right amount, specifically if it causes the signal's phase to shift by 180 degrees, then our beautiful negative feedback flips and becomes positive feedback. The subtraction turns into addition. The signal that was supposed to be correcting the error now reinforces the error, which makes an even bigger error, and on, the whole system runs away in this vicious cycle. And just like that, your precision amplifier has turned into a loud, useless noisemaker. It's oscillating.
So how do you stop this from happening? Well, engineers have a critical safety metric they live by called phase margin. You can think of it as your safety buffer. It's a measurement of how far away you are from that dangerous 180-degree tipping point right at the frequency where things can go unstable. It's your stability buffer zone.
And yep, there's a magic number for safety here too. As a rule of thumb, designers are always aiming for a phase margin of at least 45 degrees. If you have less than that, you are flying way too close to the sun. The circuit might not totally oscillate, but it's going to be unstable, ringy, and just plain unreliable. 45 degrees, that's the gold standard for a robust, stable design.
Okay, so what do you do if your design is unstable, if it's right on the edge of oscillating? You don't scrap it. No, you actively engineer it to be stable. This process is called frequency compensation, and it's really the final piece of this whole puzzle.
It's actually a pretty clever trick. An amplifier has these natural tipping points in its frequency response. Engineers call them poles. These are spots where the gain starts to drop and that signal delay starts to build up. If those tipping points are too close to each other, you're headed for instability. So using a technique called pole splitting, engineers deliberately and strategically move one of those tipping points way down to a much lower frequency. This forces the amplifier's gain to start rolling off nice and early, long before the signal delay can get anywhere near that dangerous 180-degree point. It's basically like building a speed bump early on the road to prevent a crash way down the line.
So, let's wrap this all up. What are the big ideas to take away? First, negative feedback is all about a trade. You give up raw, messy gain for beautiful, precise control. Second, that control gives you amazing benefits: predictable performance, more bandwidth, and a cleaner signal. Third, everything, and I mean everything, revolves around that one magic number, the loop gain, A times beta. And finally, while feedback is this incredible tool, the ultimate challenge for any designer is taming its dark side, that risk of oscillation, by using careful design and frequency compensation.
And that kind of leaves us with one last question to think about. If this is all just a constant trade-off between power and control, what does the perfect amount of control even look like? The truth is, there is no single right answer. The perfect design is always a compromise. How much power are you willing to give up for rock-solid stability? How much bandwidth do you really need? Finding that perfect balance, that's the true art of analog circuit design.